Hello guys, and welcome back to my channel Civil Construction and Tutor. And in this video I will show you how to design a rectangular footing. Design a rectangular footing for a column of size 600 by 400 mm carrying a live load of 2000 kN. The bearing capacity of soil is 150 kN per meter square. Take M20 grade of concrete and Fe415 steel. So basically we will design a rectangular footing for a rectangular column. In general, we will design a square footing, but as of now we are designing a rectangular footing for a rectangular column of size 600 by 400 mm. So in this method, that is, we are designing a rectangular footing with equal projection. So that means it will be different than that of the footing designing with unequal projection. So I'll point out the difference in the process while I'm designing the rectangular footing. So we are given with the service load. Don't get confused, we are given with a service load, so that is unfactored load. So this is 2000 kN. We have characteristic strength of concrete 20 Newton per mm square. Yield strength of steel is given as 415 Newton per mm square. Soil bearing capacity is given as 150 kN per meter square. Similarly, BC, that is the longer side of the column, which is 600 mm, and the depth of the column is given as 400 mm, which is the shorter side of the column. The very first step I will do is to find depth of foundation. This is not mandatory, you can directly take 1.5 meter if you want, but just I'm trying to show how the depth of the footing is calculated. So for this we have a formula according to Rankine's, which is depth of foundation is equal to soil bearing capacity divided by gamma soil. This is unit weight of soil, so it is not given in question, we have to assume this. So this is gamma soil, unit weight of soil, into 1 minus sin phi divided by 1 plus sin phi whole square, phi being the angle of friction in soil. This is generally 30 degree, and gamma soil for dry soil it is taken as 16 kilonewton per meter cube. So now we have depth of foundation as 150 divided by 16 into 1 minus sin 30 divided by 1 plus sin 30 whole square. So this comes as 1.04 meter. But generally in the general practice and considering the frost action, that is during cold weather, we have to provide depth of foundation at least 1.5 meter. So we'll take depth of foundation as 1.5 meter. So the very first step, that is the depth of foundation, has been calculated. So now coming back to our figure, now we can write depth of foundation as 1.5 meter. Similarly, now let us go to second step. Now we have to calculate the area required for footing. The area is calculated on the basis of the service load and the soil bearing capacity. So greater the value of soil bearing capacity, smaller the area will be required. So now for area required, we have formula service load plus self weight of footing divided by soil bearing capacity. In general practice, the self weight of footing can be taken as 10% of the service load. Yes, we can also calculate it by using the depth of foundation and the soil bearing capacity. The general formula is self weight of footing is equal to gamma W, that is weight of soil, multiply by depth of footing multiply by service load divided by soil bearing capacity into factor of safety. We'll take this as 1.25, or it can be taken as 1.3. So from this also we can find the self weight of footing. And for the self weight of footing, generally it is taken as 10% of the service load, as I have said. So 2000, which is the service load, remember service load, not the factored load. 2000 plus 0.1 times of 2000 divided by soil bearing capacity, which is 150. So this comes as 14.67 meter square. So this is the area required. And as I have said, for the approach that we are following to design the rectangular footing, which is for the economical design of the rectangular footing, it is suitable to provide footing with equal projections on either direction. Thus the reinforcement can be provided in the similar fashion to the other direction as well. That means as we are providing equal projection on either side, hence the moment on both sides will be similar or will be nearly equal to each other, and hence the reinforcement can be provided in the similar fashion and it will be much more economical to design as well. So for equal projection, as you can see, so the projection means the cantilever portion from the face of the column. So we are assuming this to be equal on either direction, and let it be L, this as B. So that means we are providing L is equal to B. Don't get confused. We are taking for, or the length of footing is represented as LF and the length of the projection is taken as L. So for equal footing we have this condition, that is LF minus BC by 2 is equal to BF minus DC by 2. Length of footing minus BC divided by 2 means this much portion. Okay. Similarly, BF minus DC divided by 2 is equal to means this portion. So this is the condition for the equal projections. And now let us cross multiply and we will get BF is equal to LF minus 0.2, and basically 0.2 is the difference between the dimension of the column, that is the width and depth of the column. Then for area we have L into B, considering a rectangular rectangular footing, and area we have calculated, the required area is 14.67 LF into B. So we have B as LF minus 0.2, substitute the value of B, so this is LF BF. Now if we take the LHS value to RHS, then we get LF square minus 0.2 LF minus 14.67. so this is a polynomial equation and we can solve this by using our calculator. So let me show you how to solve this. So from the mode you can go to equation or function and going to polynomial type, and the polynomial degree is 2. We have LF square, so A is 1, B is minus 0.2, similarly C is minus 14.67, so this comes as 3.93 and the other value will be negative. So 3.93 is the required length, and for BF it will be equal to 3.93 minus 0.2, so this comes as 3.73 meter. So the required length and breadth are 3.93 meter and 3.73. And for consideration of the workability inside, we will take a round of value. So provide length of footing as 4 meter and breadth of footing as 3.8 meter. So this will give us a difference of 0.2 such that the equal projection condition can be achieved. So hence required area is equal to 4 into 0.3, 15.2 meter square. The required area was 14.67 considering the soil bearing capacity, and the required provided area is 15.2 meter square, that is the value is greater as I have said. Okay, before that let us write down the dimension. So LF is equal to 4 meter, similarly BF is 3.8 meter, and the projection will be length, that is 3.8, and I have said these two are equal and the value can be computed as BF minus DC divided by 2. Okay, so L is equal to BF minus DC divided by 2. We have BF as 3.8 and DC is 0.4 divided by 2. this comes as 1.7 meter, so will be equal to B. So the length of the projection is 1.7 meter on either side. Now the next step is to calculate net upward swell pressure. So if we see, this is the base of the footing. Now as it is resting on the swell will exert some pressure on the base of footing. So sigma max or minimum is equal to PD by A plus mu by Z. So PD being the design force. Now it will be a factored load here, not unfactored. We are taking factored load. Mu being the moment regarding about axis x and y. Z being the section modulus. A is the area provided. So for now we are provided with an axial load only. That is, there is no moment acting on the structure. So for a column of carrying load of 2000 kilonewton, that is purely axial load only. So this term will be equal to 0. Hence 1.5 times of 2000 divided by area provided, that is 15.2. Now this comes as 197.4 kilonewton per meter square, and this should be less than that of the 1.5 times of swell bearing capacity to satisfy the bearing condition. As there is no moment, so there won't be any variation in the swell pressure along the area. So the swell pressure will be a rectangular type. Now the value of this is 197.4 kilonewton per meter square, and it is uniformly distributed on the base of the footing. Now the next step is check for bending. Overhang of the footing. So overhang of footing is equal to BF minus DC by 2. This comes as 1.7 meter, that is the projection. Similarly, swell pressure is 197.4 kilonewton per meter square throughout the base of the footing. But for bending, that we have to check. Check for bending the critical section at which the bending is to be checked, or the critical section lies at face of column. So we have to check for bending at the face of column. Considering this as the face of column, okay, and now we can consider this portion as a cantilever beam. As I have said, this is the overhang portion, and the overhang portion is subjected to a uniformly distributed load of 197.4 kilonewton per meter square, and this is distributed along this length, this much portion of the footing. Now you can take this as a cantilever portion with one end fixed, okay, from the face of the column, and it is subjected to a load, that is the net upward swell pressure. This is in kilonewton per meter square, and it is distributed along this length. So sigma into LF. Then we can get the value as in terms of kilonewton per meter. I hope you are getting my point. That is, we are assuming this cantilever portion of the footing as a cantilever beam with fixed end at the face of the column, and it is subjected to a uniformly distributed load, which will be a product of the net upward swell pressure multiplied by the length along which the uniformly distributed or along which the swell pressure is acting. For now we have uniformly distributed pressure, so swell pressure will take as 197.4 kilonewton per meter square, and UDL along overhang, as I have said, the swell pressure has to be distributed along the length of the footing, and this will come as 197.4 times length of footing, which is 4. So as I have said, for now we are providing equal projection, and hence we will calculate reinforcement for one side, and the reinforcement will be provided to the other side in the proportion of that. And now we can see, we can check the footing for bending on either side, that is along LF or BF. So if you see here, UDL along overhang sigma into LF, this will come 789.96, and if I had calculated UDL along this line or this length, that would have been sigma into BF, and BF is 3.8. so obviously UDL along the width of the footing would have come slightly smaller than this value. So as we have to check for a greater value, for a maximum limit, so I am taking LF. I hope you are clear. I am not going to check for bending along BF. So that is what I am trying to say. So I will take the maximum dimension and check for the bending. So this comes as 789.6 kilonewton per meter. So this is the UDL along the overhang. So the value of the UDL is 789.4 kilonewton per meter. Now for UDL we have bending moment is equal to WL square by 2. So this is the basic formula for bending moment at the fixed support of the cantilever projection, and the cantilever projection or the cantilever fixed end being the face of the column. So we are trying to find the moment at the face of the column. So this comes as WL square by 2, so which basically means W into L by 2, because the center, or we can say the centroid of the load is at the midspan of the UDL. So 789.6 into 1.7 square by 2, because the length of the projection is 1.7 meter. So this comes as 1140.9 kilonewton meter. So this is the bending moment at the face of the column. And also we have limiting moment, mu limiting is equal to 0.3 FCK B into XU limiting multiplied by D minus 0.42 XU limiting. So this is from the code we have IS 456 2000 page 96 annex G clause G 1.1 C. So as you can see here, this is the code I am using. Now with respect to this value, we'll compare the bending moment at the face of the column and determine whether it is to be designed as a singly reinforced or doubly reinforced. But for that we need the value of D, which is to be calculated. So D is the depth of the footing. So for depth we have to use a formula to calculate it, and considering Fe415 from SP16 table C page number 10, we have limiting moment of resistance is mu limiting FCK BD square, and for 415 it is 0.138. So now we'll cross multiply this term to this and we'll get the formula that we are using. So mx is equal to 0.138 fck bd square. So the depth required according to the maximum moment acting will be calculated using this formula. So the maximum moment acting at the face of the column is 1140.9. So 1140.9 into 10 to the power 6, converting this into Newton mm. So now let us substitute the value, and we have 0.138 into fck as 20 and the width of the section is 4000. So on solving, we get the value of depth required as 321 mm. I hope you know how to solve this kind of equation in calculator. So for consideration of one-way shear, so this is the point we have to understand. For consideration of one-way shear, the depth calculated from the bending moment may not be sufficient. So we have to take depth calculated from the moment consideration twice or thrice times greater than the value calculated to keep the footing safe in shear, one-way shear. Hence we will take a value greater than that of the depth required value from the footing, from the bending moment. So we will provide D as 650 mm, which is almost twice the value calculated from the depth required. So the effective depth will be 650 mm. Effective cover considering as 50 mm, then the overall depth of the footing will be 700 mm. So D is,
so you have to understand about the value that we have taken for
and
B basically
considering
means the resisting width.
The
in our
effective
case, that is the pad footing,
effective cover of
width
50 mm
LF is available for resisting the bending moment, but
the
whereas in the sloped footing,
effective
the resisting
depth
width
will
may
be
taken as width of the column plus the extra width, that is the offset provided in the
up to
footing.
This
that
point.
is for
So
the
basically
sloped
the
footing. So that is the difference
effective cover
while taking the value of resisting
is
width. So we have taken 4000 because the whole length
clear cover
4000
plus
meter is available for resisting the
half
bending moment
of the bar provided. Again, for MU limiting, as I have said, we have to check whether the section has to be designed as singly reinforced or doubly reinforced. So MU limiting is equal to 0.36 FCK B into XU limiting multiplied by D minus 0.42 times of XU limiting. And for XU limiting, we have 0.48 times of D for FE15 and 0.36 into 20, that is the FCK. Width of the section is 4000. 0.48 into D minus 0.42 into 0.48 D. So now substitute the value of D as 650 mm and we'll get this as 4663.2 kilonewton. So this is the MU limiting. This is the maximum moment that the section that we have provided is capable of resisting, but the moment that is acting on the footing is 1140.8. Hence MU limiting is greater than the bending moment acting on the face of the column. Hence the footing is designed as singly reinforced. So now this is the point that makes difference for the rectangular footing with equal projection and unequal projection. Since the projection of footing is equal on both directions, the reinforcement will be provided in proportion to the reinforcement calculated with the above parameters. As I have said, I have calculated the depth and other parameters considering the longer side of the footing, that is the UDL is distributed along the longer side, hence it will give the maximum value among the two dimensions, and I am calculating the reinforcement based on the maximum value, hence the reinforcement along the other side will be provided in proportion to the value that I have calculated.
So this is a Excel sheet that I have prepared, and here you can see the bending moment along the longer side we have calculated as 1140.8 kilonewton meter. But now if I consider the shorter span, then the moment at that particular section is 1083.75 kilonewton meter. So as the bending moment is smaller, then the area of steel calculated will also be smaller. So this is a simple thing I wanted to make it clear about.
So now let us go to the another step, that is the calculation of the reinforcement. So now for calculation of reinforcement, we will use a criteria from Annex Z IS 456 2000 page 96, and according to which we have Mmax is equal to 0.87 Fy AST times D 1 minus Fy AST divided by FCK B into D. Now substitute the value converting the moment in Newton mm, so we will get 1140.8 into 10 to the power 6 is equal to 0.87 times of Fy, which is 415, into AST, this has to be calculated, into 650, as the effective depth is 650, 1 minus 415 into AST divided by FCK is 20, and the width considered is 4000 into 650. Remember, we are not calculating the area of steel per meter, so the depth width is not taking, or the width is not taken as 1000. On solving this, we'll get area of steel as 5068 mm square. So the area of steel to be provided along the width of 4000 is 5068 mm square. This can be represented as 5068 divided by 4. So this will come as 1267 mm square per meter. So if you want to understand the reinforcement per meter, then you can convert in this term, that is 1267 mm square per meter. But for now I am taking directly for the width considered, that is 4000. So this comes as 5068 mm square. Alternately, you can calculate the reinforcement using this formula, which is simply the modification of this. So area of steel is equal to 0.5 into FCK by Fy into 1 minus under root 1 minus 4.6 Mmax divided by FCK into BD square into B into D. So substitute the value, you will get the value almost equal to the value that we have calculated previously. So the area of steel provided is 5068 mm square, and now let us check whether the percentage of steel provided is sufficient according to the IS code or not. So percentage of steel provided is equal to area of steel divided by B into effective depth. Don't get confused with the capital D, that is the gross depth. So this comes at 0.195%, and according to the code we have minimum 12%, that is 0.12%, which is greater than 0.12%. According to the code, we have to provide at least or minimum 0.12% of the gross area of the section. So it is okay, and we have to make sure that it should be sufficient considering the one-way shear as well. So from SP16 table 3, so mu by BD square, let us calculate this first. Mu by BD square is equal to, so mu is 1140.8, BD square, so this is 4000, D is 650 square, and we have to convert this into Newton mm. 1140.8 into 10 to the power 6 divided by 4000 into 650 square, so this comes at 0.67. So for MUBD square, 0.67, so this lies between 0.65 and 0.7. And for Fe for 15, the value or the percentage of steel should lie between 0.186 and 0.201. so approximately we are correct, that is the value is 0.19, which lies between 0.18 and 0.2. so this should be sufficient for one-way shear as well. Now let us provide the size of the bar and spacing. So providing 16 mm bar, the required spacing will be equal to width of section divided by area of steel provided divided by area of steel per bar, that is the area of individual bar. And also make sure if this value is less than 12%, then we have to consider the minimum reinforcement as well. Okay, but for now it is 0.195, which is greater than that of the minimum reinforcement required. So we have B as 4000 divided by 5068, that is the area of steel provided, divided by area of individual bar, that is 16 mm bar. The area of 16 mm bar is pi, that is d square 16 divided by 4, so this comes as 201. Now the required spacing is 160.8 mm, which is less than 180 mm. So from IS 456 2000 table number 15, so the clear distance between bar should be less than 180 mm. Percentage redistribution for 2 or from section considered, so 0, 415, it should be less than 180 mm. so the clear distance between bar should be less than 180 mm. We have 160.8, and considering the site, or that is the workability inside, will provide in terms of 150, 100, 125, 175 in this fashion. So nearer value to 160 is 150 mm, so provide 16 mm bar at 150 mm center to center. Similarly, if you want to calculate the number of bar, then number of bar is equal to width of the section, that is 4000, spacing provided plus 1. Don't forget to provide one number of bar extra for calculating number of bar. So this comes as 4000 divided by 150 plus 1, 27.6. so almost we can provide as 28 NOS, 28 number of 16 mm bar.